Good afternoon, gentlemen. This is going to be a lecture that's going to review everything we've gone over in our Unit 7 over motion. Below in the comments are the timestamps for you so you know where to kind of hop around to get to each topic. But if you have any questions outside of this, I do encourage you to visit with me before or after school. But let's get started. The first thing that you need to know is the history of motion, and it started with Aristotle. Now, Aristotle, he was a Greek philosopher, and he philosophized that there was two types of motion. We had a natural motion and a violent motion. Now, natural motion occurred without a force, so an example of that could be when a puff of smoke rises or a feather falls to the ground. It's something that is out of our control. It just happens. So, if I was Aristotle, I could say, if a book fell off of a desk, that the gravity pulling it down could be a great example of that natural force because I'm not causing that force to be pulled down. But he also hypothesized that we had this other type of motion that we called violent motion. And this was produced by pushes and pulls. So this was always our imposed motion. So if I wanted to go push my friend, that would be a violent motion. Or if I wanted to go push a grocery cart, that would be considered a violent motion. Now, when he came up with natural motion, he said objects fall because they're going to a more natural resting place. Aristotle did not know about gravity. However, he did hypothesize that heavier objects would fall faster than lighter ones because they would weigh more. The other one was violent motion, and this is that one that requires a push or pull by humans and or animals. So he said that violent motion had to happen because of a human or an animal, and it required a force. So our natural motion was it just happens, the object wants to go to its natural resting place, and violent motion was I'm doing it or a dog is doing it. Now, a century later, Galileo came along, and everyone was listening to what Aristotle hypothesized, but Galileo was the first one to question it. He was the one that went over the Leaning Tower of Pisa with a bowling ball and a feather, and he did some experiments about if I drop these, will the bowling ball land first because it weighs more? And he was able to see that, no, they landed relatively at the same time. So what he said was that force is not necessary to keep objects in motion, and force is needed to start, but not needed to keep it moving. So we have to overcome something. So this is where our motion principles come from, where objects moving tend to stay in motion without any extra force. So if I were to push a ball, it's going to stay in motion unless it's acted on by a different force. And an object at rest tend to stay at rest. So think about in your bedroom, you probably have your books and stuff on a table. Those ones aren't going to move unless you're actually going and pushing it or making it move. The property of maintaining your current state of motion is called inertia, and that's a topic or a concept that you need to understand. So the object wants to maintain whatever motion it's in, whether that is at rest or if it is moving. Now, with the idea of motion, this is where we get scalars and vectors. Now, scalar is a measurement with no direction, whereas vector is a measurement with direction. So with scalar, so when I talk about scalar, I'm going to have a dot, whereas my vector is my direction. Now, the next important thing that you need to understand is force came out of this. Now, force is defined as a push or a pull, and our unit for it is always going to be in newtons. And this is where we have our four types of forces. We have our force applied, our force of friction, our force of gravity, and our force normal or natural. What you need to understand is how do I draw a force diagram. So my force if applied is always going to be the direction of that push or the pull. The opposite or opposing force to force applied will always be my friction force. We always have gravity pointing down, and then we always have our normal force that just kind of counteracts our gravity force. That's what's keeping us up on the ground. So what you need to understand is how do I label my forces on a force diagram for the test. Now, force of friction occurs when one object rubs against something else. So sometimes we'll be talking and I may have a frictionless surface. So this is causing whatever item I have to not change its speed or acceleration in any direction because I wouldn't have friction. But if I do have friction, then it will occur that object's going to run against it and it's going to start slowing down. We're going to see this with all of our solids, liquids, and gases. However, in this class, we're really going to focus with it in solids. Now, friction is always going to act in the opposite direction of my applied force or that motion. So it's always opposite of my force applied. Now, understanding the direction of the arrows is extremely important when you're calculating net force. Net force has to deal with the total force acting on an object. So if I have two arrows in the same direction, I'm going to add, and if I have two arrows in the opposite direction, I'm going to subtract. So for example, for this first one, I have two arrows that are going in the same direction, and they're both at 5 newtons. So I'm going to add them together to get 10 newtons of force. When I go down, I see that I have two arrows in opposing directions, so instead I'm going to subtract them, and I'll get 0 newtons of force. And then in this case, I have two arrows except different numbers of forces, so I'll take my 10 minus 5 to get my net force of 5. So you do need to note about equilibrium is that there's two places that we can have equilibrium. Equilibrium is always going to be when our net force is equal to 0. Now this can occur when an object is at rest, or if an object has constant speed. So you need to understand that these are the two types that we can have equilibrium. Now let's do an example of a force diagram together. As a reminder, we have our 4 types of forces. We have force applied, force of friction, force of gravity, and force of normal. So when I do this, my easy go-to is I like to say, okay, here I'm kicking a ball. So in this case, I'm going to kind of make it as if the foot is coming this way for you. My force applied is going to be in the direction that I'm pushing my ball away. So here's my force applied. And I know opposite of my force applied is always my force of friction. So I'm going to put that down. Once I have these two down, my next step is I'm going to put my gravity. My gravity is always straight down, and opposing that will always be my force normal. The last thing that you need to know is if I ask you to give me what is causing it, you just need to do, in this case, my foot is causing my force applied, and that is all I need. Now there are other kinds that we can do of force diagrams. For example, we can have ones that we're going to have triangles with. So I can say I have a boat that is traveling north and experiencing a force applied of 85 newtons. A wind is coming from the east and suddenly hits it with a force of 14 newtons. What is the net force? In this one, I'm going to be actually illustrating a triangle because, and in this case I'm just going to use this triangle, I have a boat that's traveling north, and then I have a wind coming from the east. My boat that is traveling north, let me do this, has a force of 85 newtons. And my one that's coming from the east, has a force of 14 newtons. I need to find the C value. To do that, I'm going to plug this into a squared plus b squared equals c squared. My a squared was equal to 85, so I do 85 squared, plus my b squared value, which would be my 14 squared, and I set that equal to c, because my c is my unknown. My next step is I'm going to go in my calculator and solve for 85 squared. I get 7,225. I need to get my 14 squared, which is 196, and I still have this set to just my c squared. Now that I have that information, I'm going to add up my 7,225 plus my 196, and I get 7,421. Now notice I have a square up here. To get rid of that, I have to go through and square root. That cancels out both of those values to give me c, And so I take the square root in my calculator of 7,421. I'm going to round to 2 decimals, and I get 86.15 newtons. Now what's important is you do have to make sure that you're adding a direction for this value. So in this case, my boat would be veering kind of this way because the wind is coming from the east to push it. So I have a direction of northwest. Now we're going to discuss motion graphs. The general tips for motion graphs is that you're going to see a couple different kinds. One example is you might see a curved line such as the 2 that I have drawn below. These are always going to symbolize changing speed. And if I am moving away from my x-axis, that means I'm moving away from where I started. And if I'm moving towards, I'm moving towards where I started. The next kinds that you will see are flat or horizontal. These ones mean that I'm at rest. I'm not having any motion, but I am could be away from where I started. The only thing you need to know is that it's really at rest. And the last one is if I have straight lines such as these, the same idea is going to go with our curve, where if I'm moving away from my x, I'm moving away from my start. If I'm moving towards my x, I'm moving towards my start. The only thing that you need to know is that these will mean I'm moving at a constant speed. So if I were to look here to compare them, if I looked at this orange line first, I'm going to be slowing down and moving toward my start. If I'm at this green one, I'm a fast, steady speed, and I'm moving away from my start. If I'm this red one, I have speed where I'm moving away from my start, but then I'm going to go on and I move to a rest position. And then I start returning or moving towards at a constant speed to my beginning. And the last one is, even though it's a subtle curve, this is a changing speed and I'm still moving away from my start. Now let's discuss speed. Speed is not just slow and fast, and we calculate this with the following equation. We calculate speed with distance over time. With that equation, we do have 3 kinds of speed. We have what we call our average speed. The average speed is the total distance covered with the total travel time. If I give you more than one variable, so let's say I start at a distance of 0 meters, how about 10 meters, and I move to a distance of 20 meters, and I travel in a time of 5 seconds, if you were to calculate this, you would need to take your 20 meters minus my 10 meters to get the total distance covered. You will only do this if I give you more than one variable. The next one would be my constant speed. My constant speed, I'm going to have no change in the amount of distance covered in that set time period. So you don't really need to calculate this. What you just need to know is that it's constant. So kind of think about cruise control when you go on vacation with your parents. And the next kind is instantaneous speed. This is the speed, and this is important. It's at any given instant. So it's at one point. So think about when a cop is trying to catch people who are speeding. They use a radar gun speedometer. They're sitting in that one location. They are not focused on any other points of that trip. They're focused on that one point. So if I were to give you on a graph, for example, you would be solving for the distance over time at that single point. So let's do a sample problem. Let's say you travel 400 kilometers in 6 hours. What is your average speed? So what I need to do is I need to identify my distance and my time. In this case, I'm traveling 400 kilometers, so I put my 400. And I travel in 6 hours. So to find my speed, I'm going to take my 400 divided by 6. And I get 66.67 kilometers per hour. That is my average speed. Now, I could ask you to convert this. So let's do a sample of how do I convert if I have two different variables. Now remember when I do my conversions, we did these in class, I will start with a 45 meters per second to kilometers per hour. So I like to write what I start with. And what I start with, we write it in a ratio where I put meters on the top and I put 1 second on the bottom. Now I want to end in kilometers per hour. And it's really difficult to go straight from here to there. So what I'm going to do is I'm going to be setting up two different fractions. The first one, I want to go from meters to kilometers. So I use my King Henry doesn't usually drink chocolate milk. Excuse me. And I'm going to see and use that to get my numbers. My first step is I need to figure out where am I putting my meters. Now I want to cross cancel my meters, so I'm not going to put it at the top. I'm actually going to put it on the bottom so I can cross cancel them out. Where I want to end up goes on the top. Now, looking at my two variables, I need to identify which one is closer to the K. That will be my big number. In this case, my kilometer is closer to the K because it's at K. And then I'm going to do my humps. And each hump represents a 0, so I have 1,000 meters in 1 kilometer. I'm going to end up with kilometers at the end, so I know I have this part checked. Next, I need to get my seconds to hours. Same idea. I'm going to put seconds on top because I want them to cross cancel out, and where I want to end up goes on the bottom. My next step is I need to do my conversion. I need to identify what is bigger, hours or seconds. In this case, hours is bigger, so I put a 1. And we did this conversion earlier. We know there are 3,600 seconds in 1 hour. So my units cancel out. I'm left with where I want to end up. And my next step is to multiply across, divide by the bottom. So in your calculator, you would take 3,600 times 45 times 1, and you would get 162,000. And next I would take 1 times 1 times 1,000 and put that on the bottom. Now I'm going to take my 162,000 divided by 1,000, and I get 162 kilometers per hour. That is all I need to do for a conversion. Next, we're going to talk about velocity. Now, velocity is the speed of an object in a particular direction. Because it's the speed, to solve for velocity, I'm still going to use distance over time. Except this time, my final answer has to include a direction. So let's try a sample. Here, I'm going to use my velocity is equal to distance over time. I need to identify my variables. So I travel 645 kilometers north in 7 hours. What is my velocity? My first thing is I identify that I have a d value, I have a time, and I also have a direction. So now all I need to do is plug it in. My velocity is equal to my distance, which is 645 kilometers, over my time. I'll solve this the same way I solved for my speed, and I get 92.14 kilometers per hour, except now I have to include a direction. To do this, I can do N, I can do north, or I can add an arrow going up. But I must include a direction in my final answer for it to be a velocity question. So now that we've had the opportunity to try it, when I say constant velocity, I'm talking about a constant speed. However, I have to have no change in direction when I have a constant velocity. So think about driving on a highway with cruise control. However, if I'm walking in the halls to, let's say, the front door at the end of the day, I wouldn't have a constant velocity because I'm going to be turning down halls. Now, when you're running laps in gym, you could have a constant velocity if you're running straight across a football field, but the minute that you turn around, you no longer have a constant velocity because you're changing your direction. Now, this leads into speed versus velocity. Velocity is a vector. That means I'm going to have direction, and speed is a scalar where I'm going to have no direction. However, when I'm giving the answers, I'm going to use the same units, and I'm always going to use distance over time to solve. Now, a positive velocity would mean I'm moving forward, and a negative velocity means I'm moving backward. This is extremely important to understand and know the difference between velocity, positive and negative, versus acceleration, positive and negative. And last but not least, let's discuss acceleration. Acceleration is a rate of change of velocity. This is considered a vector, so I do have to include direction in my final answer if it is given to me. Now, the units for acceleration are meters per second squared, and this is where you need to understand our positives, our negatives. If I have a positive acceleration, it means I am speeding up, and if I have a negative acceleration, it means I'm slowing down. The acceleration equation is v of f minus v of I, or velocity final minus velocity initial, all over t of f minus t of I, or time final minus time initial. So you do have to solve for velocity if it's not given to you to get acceleration. But it is important that you put whatever you end your velocity in first, because if you're slowing down, you need to have a negative acceleration. But if you're speeding up, then you would have a positive, where you'd have a bigger number for your final minus a smaller number. Why don't we try a sample? So in this case, I have an initial speed, so here's my velocity initial of 20 meters per second, and then I'm going to increase my speed. That tells me I'm going to have a positive acceleration, and I increase that to 35 meters per second. That's my VF. I overall have an acceleration of 5 meters per second. How long did it take you to accelerate? Now, this is a little bit different because we've had experience, where in this case, I know that I'm finding the t value of my acceleration equation. So essentially what I'm going to do is I need to solve for t. To do that, I need to get t on its own, so I multiply it through. I need to get t on its own, so I divide my a. So I get something that looks like t is equal to vf minus vi all over a. Now that I have that filled out, I'm just going to plug in the information. I have my vf, it is 35 meters per second. I have vi, which is 20 meters per second. And it's all over an acceleration of 5 meters per second squared. Now my first step is to take 35 minus 20. I get 15 over 5 meters per second squared. And then I end with 3 seconds because I take 15 minus 5. This is a harder question. However, if you feel good and you're able to do the equation just like this, then you will be perfect and ready for the test. Now, acceleration can be described as gravity or g as well if I'm doing a free fall. When I'm doing free fall, I'm not going to count the friction from air. I'm only going to focus on the resistance where it's equal to 10 meters per second or 9.8 meters a second. And what you need to understand is the greater the mass, the stronger the gravitational pull that you will have. So you need to understand that 9.8 is my gravity number, and that if I have a greater mass, then I'll have a stronger gravitational pull. But it'll always be at 9.8 meters per second squared. Now, the acceleration on an object depends not only on the force, but also the inertia, or my resistance to motion. Sorry, that was kind of like a quick movement there. Now, the ratio of weight to mass for freely falling objects is equal to a constant g, or gravity. However, what I really want you to focus on is how do I calculate acceleration. So there we had a lot of information. The timestamps again are below if you'd like to go back and review anything. However, I do wish you good luck on your test tomorrow. And any questions you have, please make sure that you come and see me so I can help you. I hope you have a wonderful day. Bye.